Hello Sajjad, Hassan, Miss Leila and Muhammad. Alaikum Assalam. In this session, I review some definition that you know and we need for the dual of LP spaces, okay? This is the definition of norm vector space. A norm on a vector space V over F over or scalar field F, okay, is a function such as this from V to this interval such that we have these properties. The norm of F equal to 0 if and only if F equal to 0. The norm of alpha F equal to absolute value of alpha multiplied by the norm of F for all scalar alpha and F in V. And finally, the norm of F plus C is less than or equal the norm of F plus the norm of G, and this is triangle inequality. This is very important in norm space. So that this function must be have these three property, okay? A norm vector space is a pair V and this function where V is a vector space and this is a norm function on V. We see the definition of vector space in the previous session, okay? Vector space. So that this V must have an addition operation and also an scalar multiplication, okay? Example, on Fn, I remember that Fn equal to Fn equal to F this F, or we can write for example by this, okay? And this is the set of all function from the set of all function from this to F, and this is equal to if F equal to R, this is equal to this multiplication n type, okay? And if we consider F equal to complex number, this is equal to this product space, so that if m equal to Rn or Cn, okay, Rn or Cn. Now you see two norm in this space. It is very easy that if n, for example, this product space is a vector space, okay? Now we can define this norm on Fn, the norm of this entry equal to this summation, and the norm infinity equal to the maximum of this absolute value of real numbers. Then these two are norms in Fn, and it is very easy. On L1 we can define a norm. L1 defined in this example, I remember this for you. L1 equal to the set of all sequence such as this. Okay, all sequence in complex number such that this summation is finite. Okay, this summation is finite. Now, if we define this summation as the norm of this function or this sequence, then this is a norm on L1, and if we consider X as a non-empty set, Bx is the subspace of Fx, and Fx equal to the set of all functions from X to F. Okay, let Bx is the subspace of this, consisted of the bounded function from X to F, so that Bx equal to the set of all F from X to F, such that F is bounded. And this is equal to the set of all F in Fx, such that there exists one M by this property for each X in X, for each X in X, F of X is less than or equal N. Okay, is less than or equal N. This F is called bounded function. Now, if we consider this norm on any element of B of X. Norm of F equal to the supremum of this absolute value. Then this is a norm, and we can check norm properties for this function. It is easy, but please note that if we consider this norm for any f in Bx, the norm of f or norm infinity in some of books write norm infinity or norm uniform. Okay, this norm equal to this supremum. Okay, since f is bounded, this set f is bounded, so this set is bounded. This set is bounded from above okay, so that this supremum belong to R. The supremum of this set is an element in real numbers. Okay, and we define the supremum as the norm of f, so that this is an real number, and so this is a function from x to 0 infinity. All of these are real numbers. Okay, and this is well defined. For this reason we consider this subset of f of x, not whole of this. Okay, we consider element in B of x, bounded function on x, because we must this supremum to be in R. Okay, and this is a norm s raised to. As another example, let's see of 0, 1. Denote the vector space of continuous function from the interval 0, 1 to f. Continuous, not bounded. Okay, and then define this norm on this space. Please note that this is a vector space 2. This is a vector space 2. C of 0, 1 equal to the set of all f to f equal to R or C. Okay, such that f is continuous. Okay, continuous. It's very trivial that this is a vector space by these two operations, f plus c equal to f of x plus g of x, and alpha f of x equal to alpha f of x. This is the vector space by these two operations. Now we define the norm 1 of f equal to this integral. Because we know that d lambda, okay, if we consider the Lebesgue measure on this interval by lambda, this is interval d lambda, okay? Lambda is the Lebesgue measure of real numbers. Then it is easy to see that this is a norm 2 because this equal to 0 if and only if this integral equal to 0, and this is hold if and only if f equal to 0 lambda almost everywhere, and we consider almost every equal function at the same, and this is very trivial that this is this integral and this is equal to this integral, and this is equal to this norm, and also this norm equal to this integral, and this is less than or equal this integral by triangle inequality in absolute value real numbers. But this is equal to the first integral plus the second integral, okay? And this is equal to this norm plus this norm. Okay? So that this is the norm, and we have a norm space. Okay? We have this norm space. And in this example, we consider L1 of R denote the vector space of Borel or Lebesgue measurable functions f such that this integral is finite and lambda is Lebesgue measure on R, and then define this norm by this equality. Then we see that such as this, if the norm 1 of f equal to 0, define this, okay? So that norm 1 equal to 0 is equal to f equal to 0 lambda almost everywhere. And since we consider almost every function equal, this class equal to 0, and we denoted this class by f itself, so that we can write f equal to 0. Okay, please note that. In L1, if f equal to g lambda almost everywhere, we say that f and g are equal, and this class equal to the set of all g such that f and g are equal. We consider this equivalence class, so that this is this class, not f, and we write by this f for simplicity. Okay, and another example such as this on Rn or Cn. This is a norm again. Norm space or metric spaces. Suppose V and this is a norm vector space, and define V from this multiplication to 0 infinity by this definition. D of f and g equal to the norm of f minus g. Then D is a metric, and this is very, very easy. You can see this proof. So that any norm space is a vector space. Okay, any norm space is a vector, is a metric space by this metric function. And the definition of Banach space, a complete norm vector space is called Banach space. So that a Banach space is a vector space such that any Cauchy sequence converge in X. Okay, any Cauchy sequence converge. I remember that a sequence in this norm space is Cauchy if and only if for each epsilon there exists a natural number such that for each n and n great or equal n, this norm is less than epsilon, and the limit of xn equal to x if and only if for each epsilon there exists a natural number such that for each n great or equal n, this distance is less than epsilon. Then we say that if n is a converse sequence, it is very easy that any converse sequence is a Cauchy sequence. No? If any Cauchy sequence in X have a limit then we say that X is a Banach space. So a Banach space is a complete norm space. Okay, norm space, complete norm space. Any Cauchy sequence have a limit in X. And these are examples of Banach spaces. C01 by this norm, L1 by this norm. And this is an example that is not Banach space. C of 01 with this norm is not Banach, but by sup norm is a Banach space. And L1 with this norm is not a Banach space. That you see this example definition: infinite sum in a norm vector space. Suppose this is a sequence in a norm vector space such as V, then this summation is defined by this limit. This is very important because these elements are not in real number or complex number. These are in a vector space V. These are vectors, okay? But we can define this summation by this definition because V is a vector space, so that this summation belongs to V, okay? This summation belongs to V. If we consider this, for example, in V, for each natural number, this summation is an element of V because V is a vector space and this summation must belong to V. And this is equal to this summation come from 1 up to the n, okay? Now if we define this, for example, as Sn, the limit of Sn or the limit of this summation sorry, n defined by this series or summation from 1 up to the infinity. This is this limit because all of these are in our vector space V. If this limit exists, in which case the infinite series is said to converge. Okay. We have this proposition. If for any sequence with this property we have this summation is converge, then X or V is a Banach space and vice versa. Suppose V is a norm vector space, then V is a Banach space if and only if the sigma converge for every sequence such as this in V with this property. For any sequence, if this implies this, then V is a Banach space and we have the converse of this proposition 2. Okay, and this proof is very easy. And we have the definition of bounded linear maps. Suppose, sorry, dear students, do you have my voice? Dear students, do you have my voice? Okay, thank you. Suppose V, W and W are vector spaces. A function T from V to W is called linear if we have these two properties, T of F plus G equal to T of F plus T of G for all F and G in V, and T of alpha F equal to alpha T of F for all scalar number alpha and any F in V. A linear function is often called a linear map. Okay, a linear function often called a linear map. The set of all linear maps from a vector space V to a vector space W is itself a vector space. Using the usual operation of addition and scalar multiplication of function. Okay, the set of all linear maps that we denoted by L of B and W or of B. Okay, bounded linear map from V to W denoted by this. Okay, so that if we define T from V to W the norm of t from v to w by this equality, the norm of t equal to the supremum, then we call it this t bounded if this norm be finite. Okay, this norm is finite, and the set of all bounded linear maps from v to w is denoted by these. So that B of V and W equal to the set of all F from V to W such that F is a linear map and F is bounded, or the norm of F or T, okay, be finite. This norm, the supremum of all TF such that F belongs to V and the norm of F is less than or equal 1. This definition is very important. The norm for any T, for example, in this space, let me write all of this T okay by the book symbols T, T and T. The norm of T is defined this supremum f of x such that x belongs to V and the norm of x is less than or equal 1. Norm of Tf or Tx. Okay. For example, if we consider this norm vector space by this norm function, the norm of f equal to the supremum of f on this interval, and define this T Tf of x equal to this, because we know that T, if we consider T from this to itself, for any f in this space, T of f is a function in this space, so that for any f in this space, T of f is a continuous function on this interval, so that T of f is a function from 0, 1 to f or to c. Okay? Note the function role of this function defined by this. T of f of x equal to x2 f of x. Okay? x2 f of x. So that this is the function role of this function. And then T is bounded linear map and the norm of T equal to 9. As we should verify, because if we want this norm this is equal to this supreme. And this norm less than or equal 1. But for any f in this space, we see that this norm equal to this supremum. Okay? Tf is this interval, and this is equal to this supremum x2 x belong to this interval. And this is if we consider this f, this norm is less than 1, this is equal to this supremum. Okay? If we consider this is less than 1, then we see that this is norm. Okay, this norm is less than or equal this supremum and this is equal to 1. Oh, sorry, this is 0, 3. Okay. Okay, let me complete this and take another example. so that all of these is less than or equal 1, and so this norm is less than or equal 1. And if we consider constant function 1, we see that t of 1 the norm of t of 1 equal to 1. This 2 shows that the norm of t equal to 1. Now as another example, if we consider t from 0,3 to C03 by the same function rule, t of f equal to x2 f, this function rule, then if we consider this, then the norm of t equal to 9, because again the norm of t equal to the supremum, f belong to this space, and norm of f is less than or equal 1. But for any f in this space, we see that the norm of tf equal to the supremum tf of x belong to this interval 0, 3, 0, 3, okay, 0, 3, and this is equal to the supremum x2, x2, this absolute value x belonging to this interval, and this is less than or equal the supremum of x2, x belonging to 0, 3, and this is less than or equal 9, because f of x is less than or equal 1. All of these absolute values must be less than or equal 1. Okay, and similar to this, if we consider the constant function 1, we see that this supremum equal, please note that all of these is less than or equal 9, so that this supremum must be less than or equal 1, and finally the norm of t equal to 9. Let me write better. This norm equal to 9. Okay, And we can see other examples. Such as this. Let B be the norm vector space of sequence in F such that AK equal to 0 for all but finitely many. And we define this norm the maximum, and T by this function rule, T of this sequence equal to this sequence. It's very easy that this is an element of V again. Please note that V for example equal to the set of all sequence such as this, okay, or we can write simply this sequence, okay. In all scalar field F such that there exists an natural number such that for any I period or equal k, a k equal to 0, okay. So that this sequence have this property that from one index up to the n, all of this must be 0. Now it is very easy that this is a vector space, and we can define norm on this vector space. A1, A2 up to the n equal to the maximum of this absolute value, okay. I write maximum instead of supremum because this is a finite set. All of these for k and greater than k equal to 0, so that this is the maximum of this set. For example, A1 and AK, all of this equal to 0, okay. Now we define T from V to V by this function rule, T of this sequence A2, A3 up to the n equal to, please note that this or function or element in V, okay. For example, T of this A1, A2 up to the n equal to this A1, 2, A3, A3 and A1, 2, A2, 3, A3 up to the n. We see that this is an element of V again, okay, because if from k up to the n equal to 0 in this sequence, from k up to the infinity equal to 0 in this sequence too. Okay, and this T is a linear map that is not bounded. This T is linear, this trivial that is linear. Okay, for example, T of A1 A2 plus, let me write by another color so that this A1 A2 plus B1 B2. Okay, this is equal to T of this. A1 plus B1 A2 plus A2 B2 up to the n, and this is equal to this sequence A1, sorry, okay, A1 plus B1 and 2 A1, sorry, A2 plus B2 and 3 A3 plus B3 up to the end by this function rule. Okay, by this function rule, A1, 2A2, 3A3, and this is equal to these two, A1, 2A2, 3A3 plus B1, 2B2, 3B3, and this is equal to okay, by this function roles, so that we have this linearity of this function. Okay, T of this plus T of this, and similarly T of alpha A1 A2 up to the n equal to alpha T of A1 A2 up to the n, so that this T is linear, but this is not bounded linear map, because the norm of T equal to the supremum T of A1 A2 up to the end, such that this norm is less than or equal 1. And this is equal to infinity. This is not bounded. It is infinity. Because, for example, if we consider this element for example, zero, zero, 1, 0, 0 up to the end. If you consider this as an, for example, okay, this is the S entire in this sequence, okay? Then we see that this norm equal to 1, so that we have this equality. But the norm of T of an equal to this norm, 0, 0, n, because we have A1, 2, A2, 3, A3, and in general A and A, okay? Sorry. This is n multiplied by 1 and 0, 0 up to the n, and this is equal to n, so that we have any natural numbers in this set, and so the supremum must be infinity, okay? So that for each n in n, this norm is greater or equal n, so that this norm equal to infinity, so that this is an unbounded function, okay? Let me review this two proposition for you. This is a norm on B of V and W. Suppose V and W are normed vector spaces, then we have this inequality, and this for all S and T as bounded linear maps. And furthermore, this is a norm on this space. This proof is very easy, because please read this. And also, this is a Banach space if this second space is a Banach space. Suppose V is a norm space and W is a Banach space, then this is a Banach space. This V is not important for completeness of this space, but this is very important. And this is its proof. Its proof is very easy, because we use only the definition of completeness. Please read this. And finally, a linear map from one norm space to another norm space is continuous if and only if it is bounded. Continuity and boundedness are equal. Please read the proof of these three theorems. These are very important. Okay, dear students, I think it is enough in this session. We will continue in the next session. Do you have any question? Do you have any question, dear students? Okay, thank you for attention, and goodbye for now.